And now I will discuss about Ampere's Circuital Law. First, I will discuss about Ampere's Circuital Law. In classical electromagnetism, Ampere's Circuital Law, discovered by André Marie Ampere in 1823, relates the integrated magnetic field around a closed loop to the electric current passing through the loop. James Clerk Maxwell derived it again using hydrodynamics in his 1861 paper on physical lines of force and is now one of the Maxwell equations, which form the basis of electromagnetism. After solving a number of simple electrostatic problems with Coulomb's law, we found that the same problems could be solved much more easily by using Gauss' law whenever a high degree of symmetry was present. Again, an analogous procedure exists in magnetic fields. Here, the law that helps us solve problems more easily is known as Ampere's Circuital Law, sometimes called Ampere's work law. This law may be derived from the Biot-Savart law, and the derivation is accomplished. For the present, we might agree to accept Ampere's Circuital Law temporarily as another law capable of experimental proof. As is the case with Gauss' law, its use will also require careful consideration of the symmetry of the problem to determine which variables and components are present. Ampere's Circuital Law states that the line integral of H about any closed path is equal to the direct current enclosed by the path. The magnetic field in space around the electric current is proportional to the electric current which serves as its source, just as the electric field in space is proportional to the charge which serves as its source. We define positive current as flowing the direction of advance of a right-handed screw turned in the direction in which the closed path is traversed. Referring to the figure, it shows a circular wire carrying a direct current I. The line integral of H about a closed path, lettered A and B, results in an answer of I. The integral about a closed path, C, which passes through the conductor, gives answers less than I, and is exactly that portion of the total current which is enclosed by the path C. Although paths A and B give the same answer, the integrands are different. The line integral directs us to multiply the component of H in the direction of the path by the small increment of path length at one point of the path, move along the path to the next incremental length, and repeat the process continuing the path is completely traversed. Since H will generally vary from one point to point, and since path A and B are not alike, the contributions to the integral made by, say, each micrometer of path length are quite different. As a second example of the application of Ampere's Circuital Law, consider an infinitely long coaxial cable transmission line carrying a uniformly distributed total current I in the center conductor and negative I in the conductor. The line is shown in figure. Symmetry shows that H is not a function of phi or z. In order to determine the components present, we may use the results of the previous problem. A circular path of radius ρ, where ρ is larger than the radius of the inner conductor, but less than the inner radius of the outer conductor. Magnetic field strength variation with radius as shown for a coaxial cable in which B equals 3A, C equals 4A. It should be noted that the magnetic field intensity H is continuous at all the conductor boundaries. In other words, a slight increase in the radius of the closed path does not result in the enclosure of a tremendously different current. The value of H shows no sudden jumps. The external field is zero. This, we see, results from equal positive and negative currents enclosed by the path. Each produces an external field of magnitude I over 2 pi rho, but complete cancellation occurs. As final example, let us consider a sheet of current flowing the positive y direction and located in the z equals 0 plane. We may think of the turn current as equal divided between two distant sheets on either side of the sheet we are considering. A sheet of uniform surface current density K equals KYA is shown in figure. H cannot vary with X or Y. If the sheet is subdivided into a number of filaments, it is evident that no filament can produce an H component. Moreover, the Biot-Savart law shows that the contributions to Hz produced by a symmetrically located pair of filaments cancel. Thus, Hz is 0 also, only an Hx component is present. It follows the Hx is the same for all positive Z. Similarly, Hx is the same for all negative Z. Because of the symmetry, then the magnetic field intensity on one side of the current sheet is the negative, that on the other. Letting AN be a unit vector normal to the current sheet, the result may be written in a form correct for all Z as H equals 1/2 K times AN. If the second sheet of the current flowing in the opposite direction K equals negative KY is placed at Z equals H, shows that the field in the region between the current sheet is H equals K times A sub N equal 0 is less than Z and is less than H and is 0 elsewhere. H equals 0. The most difficult part of the application of Ampere's Circuital Law is the termination of the components of the field which are present. If the solenoid has a finite length d and consists of n closely wound turns of a filament that carries a current I, then the field at points well within the solenoid is given closely by H equals Ni over d A sub Z. It is well within the solenoid. The approximation is useful if it is not applied closer the two radii to the open ends, nor closer to the solenoid surface than twice the separation between turns. For the toroid shown, it can be shown that the magnetic field intensity for the ideal case is H equals K sub A rho minus A over rho A sub phi inside. It is an inside toroid. H0 is in outside. For the end-turn toroid of figure, we have the good approximation. H equals N times I over 2 pi. A sub rho, it is in the inside toroid, and H equals 0 sa outside. As long as we consider the points removed from the toroidal surface by several times the separation between turns. Toroids having rectangular cross-section are also treated quite readily, as you can see for yourself.